6.1, number 6. Final answer is just the expression of the integral. Hopefully you guys are grading even though you're ignoring me. That would be cool. Number 6 is the expression of the integral as you guys see. Let me go ahead and zoom in just a little bit. Number 18, because this has been up here for a while now. Number 18, the intersection points are 2, 4, and negative 3, 9. So you should have used the x's or the y's, depending on which way you were solving. I think the x way was the easiest way, because top minus bottom was the easiest, but they actually had you solving it 2 different ways just to show you it was possible. So in terms of x, you would have done top minus bottom, which would have been the line minus the parabola, or you could have done it the other way with absolute value, using your x bounds, the left and the right. The left and the right. If you were doing y's, you would have had to use the y bounds, which would have been 4 to 9, but here's the dilemma. Would 4 to 9 have covered all of the area? No. You actually had to realize the graph went all the way down to 0 in between 4 and 9. So you would have had to actually go from 0 to 4, then from 4 to 9. With 0 to 4 having been right minus left, which would be the positive square root of y, minus the negative square root of y, which is why they have 2y, because they would actually end up combining 2 root y. And then for the other region, from 4 to 9, it was a lot easier. It was the line in terms of y, 6 minus y, minus the parabola in terms of y, which would have been minus negative root y. There was a lot to figure out for the right-left, sadly. But it was possible to make the answers match. It was possible to make the answers match. Letter C. A was way easier. In terms of x was way easier. Top-bottom was way easier. So, guys, the AP is never going to force you to solve it the hard way. The reason why I assigned this one to you and the reason I think why it's in this section is because sometimes your brain accidentally chooses the hard way. And if it does, it is possible. I just don't want you to go the hard way, not realizing it's the hard way, and then do something like, oh, for 4 to 9, do the right minus the left, when you might be leaving out this whole chunk of area. So you have to be on the lookout for which one naturally makes more sense, which one's going to cover the entire region. Because from 4, this horizontal line, to 9, you're missing out on all of this area. If you go from the horizontal line 4, see, follow my mouse, up through 9, you're not hitting any of that.
Rather, why does 0 to 9 not work?
Oh, because if you do 0 to 9, you don't have one defined left and one defined right. If you were to do left as the line and right as the parabola, 0 to 9, you're going to have all this extra that you're not supposed to have. So you would need to go from one side of the parabola to the other, from one square root of y to the other, which is where this expression comes from. To get that closed-in region, then you have to go from the line to the parabola for the rest. Does that kind of make sense? Okay. So thanks for powering through number 18. I think it was a profitable exercise, even though I know some of you were like, ah. Yeah, it was painful. It was painful, but I believe it was profitable. Number 22. If you guys just went natural in the sense of finding your bounds, you would have gotten 0 and 4. The nice thing is visualizing 0 to 4 would have enclosed everything. You would have had a nice top, nice bottom. Even if you did it the other way, throw an absolute value, you would have ended at 32 thirds. 32 thirds. And last but not least, number 40 was actually a by hand problem because it was all unit circle-y stuff. Maybe you would have gone with the graphs, maybe you wouldn't, but if you had found the intersections by setting equal to each other, they would have been negative pi over 2 to pi over 6. Anti-derive, plug and chug, if you need to, absolute value, just in case you chose the wrong one on top. How'd you guys do finding the intersections? I think that's the hardest part by hand. You would have had to set this equal to that, right? How do you do that? Oh, they do? Never mind then. Yeah. I was going to say you could have solved.
Well, they gave you bounds, and it just happened
to also be the intersections. Because remember, if you didn't look at a picture, the bounds wouldn't be enough. You would have had to check there weren't any intersections in between to split up the integral. So you would have had to use the double angle of cosine to solve and then move everything to one side. So 0 would equal to 2 sine squared plus sine minus 1. Then you would have gotten 2 sine 1, 1 plus minus sine equals 1/2, sine equals -1. But if you guys remember, there's going to be infinitely many intersections, so that's why they probably had to narrow down, but they did give you the bounds. And so you could have gone ahead and double checked, are there any, in between -π/2 and π/6, are there any places where sine will equal -1? No, it's only at -π/2, 3π/2, etc. So that's fine. And then are there any places in between these two where sine equals 1/2? Well, that would happen at π/6 or 5π/6. Nope, we're good. Nothing in between. Since there's nothing in between, you could just throw the absolute values out and say, let's go. Let's solve. Final answer, 3√3/4. Yes, your calculator would solve for you 1.299, but these unit circle values, you should assume this would not be a calculator problem. This would not be a calculator problem. You could throw it in your calculator, but √3 is going to be 1 point something, and it must be enough 1 point something in order to go ahead and make this bigger than 4, so 1.299. Okay, number 82, here's our last one. Do I need to zoom in a little bit? Is it too small? They gave you the picture? Oh, that's nice. So looking at the picture, what did you guys naturally think? Top, bottom, or right, left? Yeah. Oh, don't do top, bottom. I would do right, left, and here's why. Top, bottom, you need to do vertical slivers. Remember, slivers accumulate to make area? If you do vertical slivers, wouldn't you have to go from parabola to parabola for this part? Someone said that you should do vertical and not horizontal. You should do top, bottom minus instead of right, left. I was saying if you're doing top, bottom, dx, number one, you'd have to get this in terms of x, so you'd have to solve for y. And number two, top, bottom right here would go from parabola to parabola. That would be really nasty. Ah, okay. So doing it according to y would be a right, left. And that's much nicer because the line's always on the right for horizontal slivers, and the parabola is always on the left. If you had gone between the line and the parabola top, bottom, you would have this extra area right here. You would have gotten this area too, and you don't want it. So you would have needed to go from parabola to parabola, like a plus minus square root thing. You would have had to go from one to the other. But the other problem, Sarah, is to do top, bottom. You would need it in terms of x, but we have y, so you'd have to get y by itself, which would be really hard since it's in two places, if that makes sense. So the math kind of tells us, I don't want to do anything differently. I want to use this as is. Okay, fine. Let me get him in terms of y, which they did. X is equal to negative y plus 2. Now I have both of them in terms of y. You didn't even technically need the picture at this point. Set equal, find your natural bounds, which is negative 1 and 2. Plug in one, plug in the other. One is right, one is left. Throw in absolute value bars to be safe. Solve, solve, solve. Positive 9/2. C is the final answer. So the picture was great and all. I'm not sure if it made a huge difference, but it should have, hopefully, if the picture is helpful. Horizontal slivers made a lot more sense. Horizontal slivers made a lot more sense. So letter C. Guys, you were asking each other about the odds. Are there any odds that we have remaining questions on, or any evens that you want to go back to? Nathan?
81.
Number 81. Any evens that we want to go back to? Which one? 22. On 22, did they give you guys a picture? No. Okay, so you just had these two functions. Sarah, was it okay getting the intersections of 0 and 4? Okay. And then so once you got the intersections, down here, technically, remember, they knew who was top, they knew who was bottom, but you just had to do one minus the other. And once you do one minus the other, since they're polynomials, we can rewrite, just like we can any integral, we can rewrite before we antiderive. So they went ahead and combined like terms, and that's how they got here. Because the 1 canceled with the 1, and the 3x with the minus the negative x became 4x. So then antiderive, power rule, we have a cubed over 3, we have a squared over 2, 4 over 2 reduces. Then remember, it's going to plug in the 4 to both. We're going to plug in the 0 to both and subtract. And right down here, you would have probably, like, if there was no picture, we would have had absolute value bars all along the way. Didn't need to leave them in, could have pulled them out because there's nothing in between 0 and 4. They're the only two numbers we found. So then right here, there would have been little absolute values. Once you plug in negative 64 thirds and then 32, I would have gotten thirds, which would have been 96 thirds. And remember, with absolute value, you have to put this together first, then do the absolute value. That's a common mistake. Some people would change it now. Don't. Put it together first. So you end up with 32 thirds. Then absolute value stays. Yeah, a few people just like to change all the negatives to positives, but that's not right. You have to actually find the solution and then make it positive if you need to. Does that make sense? Okay. We had two odds. Let me go ahead and get out of this, though, because these are only the evens. Let me clear off all the ink so that that's gone. And then let's go back to our notes. Okay, let's start with Charlotte, yours. It was number 50 what? 51. Did they give you a picture or no picture? Okay, with picture or no picture? No picture. So then what were the functions they gave you?
Y equals x squared and y equals 4 cosine x.
Okay. And they just say area between?
I don't know how to find the intersection.
Since it's a calculator problem, all you have to do is set x squared equal to 4 cosine x, and you have two options. One is to graph this as y1 and this as y2, and literally find the intersections, find where they cross in your graphing calculator. The other way is you could subtract to the other side, and then instead of finding intersections, you're just putting all of this into y1, and then you're just finding the zeros. Does that make sense? Both ways are totally valid, but both ways you need your calculator. And remember, in your calculator, when you solve for those values, Sean, what did you get for your two intersections for 51?
Okay, so your two intersections are negative 1.01538, probably.
1.01538?
528. 1.20. and then the next one is actually not the positive.
It's negative 1.
1.201?
And then the other one's positive. So you have to stow one of them, which I would stow the positive one. Then you could say negative a to
That's true.
a in your interval.
Since I already wrote the A's and B's, I'll just use that. But Sean was saying you can just stow one and then make the other one the opposite. But then you could just go ahead and do something like y1 minus y2. Throw it in your calculator, and then what do you end up getting as your final?
6.30.
Does that make sense?
Yeah, that's for like the number 40 is that cosine 2x 1 minus 2 sine squared. Like how do you get that?
Well, I was showing that because on that one they were unit circle values. And with unit circle values, sometimes they require you to do those by hand. So that was the double angle formula of cosine. Cosine of 2x either equals cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus 2 sine squared. I used this one because it was all sines. I didn't want cosines. And so the reason I use that, look at those values, negative pi over 2 and pi over 6. Those were unit circle. This is not unit circle. Yeah. This is a calculator problem. And then Nathan, you had one, number 80. What was it? 85? 81. Okay. What was going on there?
And they just wanted area.
They just wanted area between. What were my two functions?
Negative 2x minus 1.
Okay.
And negative x squared minus 4x plus 2. For some reason I couldn't quite find the intersection.
Okay.
I probably could have done the area pretty similar.
Got it. I'm assuming that we're going to assume top minus bottom, right?
Yeah.
Dx. So then if we set these equal to each other for our bounds, Move everything to one side. Want to get equal to 0. I'm going to move everything that way. I don't like negatives. So then it's going to be 0 equals x squared plus 2x minus 1. Oh, yeah. Minus 3. That's not too bad, because then you can just think of factors of 3 that add to be 2. There we go. It's okay. I just made a subtraction error, and that would have messed me up. So there we go. Then do the bounds, then do top minus bottom. But whichever way you go, you'll be fine. All right, bud. Hope you feel better. All right, kiddos. Go ahead and hold up your 6.1 homework. Let me see it.
I only get a half. I only did 2.2.
Oh, buddy. Ooh, look at those pictures. Look at those pictures.
It's like, too much time. Oh, my book's falling apart.
You gonna email me? Okay. 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 Good pictures. Good, Carrie. Twos, and so I was like, who's 1, who's 2 for each game, and but then I got judged, so, oh well. Here we go. I changed a few. Although, who did I have winning the first time? If they win, I'll... Anyway. 6.2a, volumes by slicing. Kiddos. When we did area, okay, that's not going to work for me. It's okay. You guys see all the pictures? I think you can have those pictures in your heads in the sense of, can't slices be put together to make a whole? Or can't a whole be cut into slices? Yes or no? Okay. It's basically what we were doing with area, but with area, we were trying to put together. Okay. Area under a curve, right? Let's say we cut it between A and B. We were trying to find the area in between. Okay, this is old school, right? A to B of f of x dx. And if you want to think about area between, we can kind of, but this one's just an old school area problem. We could say area between is between y equals f of x and y equals 0, or the bottom curve. But here's the idea. When we talked about an integral solving for us area, didn't we think rectangles? Okay. So to solve for the two-dimensional area, we would think rectangles. And the integral takes those rectangles and makes them infinitesimally thin. And so I started calling them recently, actually this year. Sarah, I think it was actually with you. I started calling them slivers. What am I talking about with slivers? What's a sliver of wood? It's like a little piece that chips off, right? Like a splinter that gets in. That would be like a sliver. Right? No, I wouldn't say a wood chip, but I mean, some people might call a wood chip a sliver. So if we were thinking of a rectangle, I mean, we can approximate these areas with rectangles, which we call Riemann sums, right? And the more rectangles we have, haven't we talked about this? The more rectangles we have, the more accurate the approximation. Now, if we were still to cut this up into, I don't know, 10, it looks kind of like there'd be 10 of the ones I've been making. If we were to cut this up into 10 rectangles, would it still be approximate, though? Yeah, if we were to cut it up into 100 rectangles, so much thinner, wouldn't it still be approximate? Yes, but theoretically, what's going on as we're fitting in more and more and more and more? The answer, or the areas, are converging to the actual area. Remember, this one, with the dx, what it says is, let's take a rectangle with a height of an f of x value and a base of a dx value. What the integral does is says, okay, you want to use rectangles? I'll use rectangles. And I'll go ahead and take function values. I'll multiply them by bases, or dx values. But what the integral does is says, I'm going to make that dx that delta x approach 0. It says I'm going to make that dx, or that delta x, because they're the same thing, I'm going to make that approach 0. And as I make that approach 0, we're no longer accumulating rectangles, now we're accumulating infinitesimally thin slivers. And as you put those infinitesimally thin slivers together, we call it accumulating. As we accumulate them, we get the entire area. That's where we've been. This is what we've already done. So how are we going to use that idea to find volume and not just area? Section 6.2 says, we're no longer accumulating slivers. Now we're accumulating slices. Now we're accumulating slices. Let me give you a quick visual of some sort of solid that we might be trying to accumulate. That's not what I wanted to do, but good thing it didn't actually obey. What if I was to give you something like this function? Cut between an A and a B. That's close, right? And let's say kind of like, no, that works. Kind of like pre-cal last year. Let's say this was being revolved. Ooh. About the x-axis. Don't necessarily have to draw it. But if we revolve it, what are we going to get? Kind of a cup, right? A bowl. And this bowl would have a volume, right? Okay, now here's the dilemma with the bowl and the volume. If I want to think about the volume, here's what I'm going to do. I'm going to go ahead and, since there's no geometric formula for this shape, sadly. It's not a cylinder, it's not a cone, it's not a sphere. Does that make sense? It's not a rectangular solid, it's not a cube. There's no geometric formula for this volume. What we're going to do is we're going to take some sort of representative point, like this one right here. We're going to, in a sense, make a rectangle. And with that rectangle, which we would do kind of with area, what we're going to do is we're going to revolve that rectangle. And when we revolve that rectangle, what we're going to take is, or what we're going to get is, that's not working. I could do it more precisely over there, but it wasn't working. If I take this rectangle, and if I revolve it, what I'm going to get is a disk. Now here's the dilemma with the disk. If I accumulate disks, is it going to perfectly give the volume that I want? No, because disks are flat. Disks don't curve. Disks are going to be flat. But here's a dealio. This is really just a cylinder. And this cylinder, I can say, has a volume formula of pi r squared h, which applied to this application would be pi, the r is going to be my f of x value. It's the height. And my height is going to be my dx. That's something I think I can put in a calculator. Or I can put, I should say, in an integral. Now let me give you some better illustrations of this. But once again, the idea is putting together slices to make a whole. But we can't just do irregularly shaped slices, because we would have the exact same problem as our irregular volume. We wouldn't have a geometric formula to help us. So the slices that we have to choose are slices that we actually know geometric formulas for. Like this one, we could do it for an orange. But with an orange, guys, do you realize the slices, put all the slices together, are they straight across like you see in this graph, or are they curved? Yeah. So I couldn't necessarily do a perfect orange slice as one of my ones to use because it wouldn't have a geometric formula. Let me go ahead and show you. I think I have the pictures right over here, if I can find them. Here we go. Oh, are you not going to work for me? Oh, sad day. This is one of those, if we had more time, I would love to do this project. In order to find the volume of a raindrop, if we were to use little baby discs, we call discs like the slice, that's a cylindrical slice, would that be a perfect raindrop or whatever this is supposed to be, egg? No, it's going to be a little segmented, like it's going to be little stair steps. But does it try to approximate the entire volume? Yes. Same thing with this vase. They're using a vase. They're using semicircular discs, which once again are geometric figures, and that could approximate. Now, once again, is it going to be nice and smooth? No, it's going to be a little segmented. It's going to be a little segmented, but it's going to be approximating the volume of the whole. So if I could actually get all these slices and accumulate them, add them, and if I could make the slices infinitesimally thin, if I could make these infinitesimally thin, the more discs I fit in, and the thinner I make them, the closer they will approximate the actual volume. And guess what mathematical calculus function can do this for me, making them infinitesimally thin and accumulating? The exact same one we used for this, an integral. Just instead of doing a base times height, instead of doing a two-dimensional area, we're going to be throwing in a three-dimensional formula of volume. But this little dx is going to be one of the dimensions. So it's going to look like areas, but with this little dx, it becomes volumes, and then the integral will make these infinitesimally thin and make it perfect where we could not. Now, do you think these kids got pretty close to the actual volume that it was supposed to be? Yeah, they were approximating. Ooh, I like the fish with the semicircles. That's kind of fun. The raindrop. Oh, there's the raindrop. That one's kind of cool. This shark, I think, is made with isosceles, isosceles triangles, I think. That's what's going on there. These ones are full circular discs, a lot of full circular discs. The turtle, who knows, maybe semicircles. But anyway, long story short is we're going to use geometric formulas, volumes that I can do, and accumulate those slices. So the goal is to find volumes of three-dimensional figures using integration. But in order to use integration, we have to know the actual geometry formulas of the slices. The nice thing is in calculus and in the AP problems, in the book problems, you'll never have to choose what slices to make. They will tell you which slices to use. I could, let's see, do a few more illustrations. I might save those until tomorrow, though, since we're kind of running out of time. Let's go ahead and get to this page. This page, it was probably kind of hard to draw or probably kind of hard to write. But what's going on in this page is that if you notice, the slices, when they are sliced or cut perpendicular to the x-axis, are always going to have little baby thicknesses of dx. And when they're sliced perpendicular to the y-axis, would technically be vertical. If this is the y-axis. If they're sliced perpendicular to the y-axis, dy. And if you remember with areas between, wasn't it important to know when to do dx and when to do dy? So these wordings are going to help us. With respect to the x, it's going to be a dx. We have to orient it that way. There is no choice. And if it's sliced with respect to the y, we're going to have to do dy. Guys, this leads us up to, if you're not going to have time to write it because we only have 1 minute left, feel free to take a picture of it. This is the forever card for section 6-2. We only started it today. For some of you, this might be enough to go ahead and go. The rest of you guys, we're going to have to wait until tomorrow to get some examples done. This is forever number 45? I think it's 45. 44 was the last one. Take a picture of it. Get it in your notes. Have it ready for tomorrow. And tomorrow we're just going to practice on how to solve. I think our test is next Friday now. I think we got off a day because of Pi Day. But we'll be all right. We'll be all right. All right, cool kids.